33. Approach and landing techniques. The flare height be reached at the appropriate airspeed and flight path angle. The ATHR and FPV are effective aids to the pilot. VAPP should be determined with the wind corrections by using the FMGS functions. When the aircraft is close to the ground, the wind intensity tends to decrease and the wind direction to turn direction in degrees, decreasing in the northern latitudes. Both effects may reduce the head wind component close to the ground, and the wind correction to VAPP is there to compensate for this effect. When the aircraft is close to the ground, high sink rate should be avoided, even in an attempt to maintain a close tracking of the glide slope. Priority should be given to the attitude and sink rate. If a normal touchdown distance is not possible, a go-around should be performed. If the aircraft has reached the flare height at VAPP, with a stabilized flight path angle, the normal SOP landing technique will lead to the right touchdown attitude and airspeed. During the flare, the pilot should not concentrate on the airspeed, but only on the attitude with external cues. Specific PM callouts have been reinforced for excessive pitch attitude at landing. When transitioning from IMC to VMC, the crew will watch the bird versus the aircraft attitude symbol in the center of the PFD. This provides a good assessment of the drift, thus in which direction to look for the runway. But, then, do not turn towards the runway. Do not duck under. 34. Flare and touchdown. Pitch control. When approaching the ground, auto trim ceases and the flare law activates. During flare, PF will have to apply a progressive and gentle back stick order until touchdown. The flare law technique is thus very conventional. Prior to flare, avoid destabilization of the approach and steepening the slope at low heights in attempts to target a shorter touchdown. If a normal touchdown point cannot be achieved, or if destabilization occurs just prior to flare, a go-around or rejected landing should be performed. The PM monitors the rate of descent and should call sink rate if the vertical speed is excessive prior to the flare. From stabilized conditions, the flare height is about 30 feet. This height varies due to the range of typical operational conditions that can directly influence the rate of descent. Compared to typical sea-level flare heights for flat and adequate runway lengths, pilot need to be aware of factors that will require an earlier flare, in particular, high airport elevation. Increased altitude will result in higher ground speeds during approach with associated increase in descent rates to maintain the approach slope. Steeper approach slope compared to nominal 3 degrees. Tailwind. Increasing runway slope. Increasing runway slope and/or rising terrain in front of the runway will affect the radio height callouts. The visual misperception of being high is also likely. Late, weak or released flare inputs increase the risk of a hard landing. Avoid underflaring. The rate of descent must be controlled prior to the initiation of the flare rate not increasing. Start the flare with positive back pressure on the side stick and holding as necessary. Avoid forward stick movement once flare initiated. Releasing back pressure is acceptable. At 20 feet, the retard auto callout reminds the pilot to retard thrust levers. The pilot must ensure that all thrust levers are at idle detent at the latest at touchdown, to ensure ground spoilers extension at touchdown. In order to assess the rate of descent in the flare, and the aircraft position relative to the ground, Look well ahead of the aircraft. The typical pitch increment in the flare is approximately 4 degrees, which leads to -1 degree flight path angle associated with a 10 knots speed decay in the maneuver. Do not allow the aircraft to float or do not attempt to extend the flare by increasing pitch attitude in an attempt to achieve a perfectly smooth touchdown. A prolonged float will increase both the landing distance and the risk of tail strike. After touchdown, the pilot must fly the nosewheel smoothly, but without delay, onto the runway, and must be ready to counteract any residual pitch-up effect of the ground spoilers. However, the main part of the spoiler pitch-up effect is compensated by the flight control law itself. It is not recommended to keep the nose high in order to increase aircraft drag during the initial part of the rollout, as this technique is inefficient and increases the risk of tail strike. Furthermore, if auto brake med is used, it may lead to a hard nosegear touchdown. Lateral and directional control. Final approach. In crosswind conditions, a crabbed approach wings level should be flown with the aircraft cockpit positioned on the extended runway centerline until the flare. Flare. The objectives of the lateral and directional control of the aircraft during the flare are to land on the centerline, and to minimize the lateral loads on the main landing gear. The recommended de Crab technique is to use all of the following. The rudder to align the aircraft with the runway heading during the flare. The roll control, if needed, to maintain the aircraft on the runway centerline. Any tendency to drift downwind should be counteracted by an appropriate lateral roll input on the sidestick. In the case of strong crosswind, in the de Crab phase, the PF should be prepared to add small bank angle into the wind in order to maintain the aircraft on the runway centerline. The aircraft may be landed with a partial de Crab residual crab angle up to about 5 degrees to prevent an excessive bank. This technique prevents wingtip, sharklet or engine nacelle strike caused by an excessive bank angle. As a consequence, this may result in touching down with some bank angle into the wind, hence with the upwind landing gear first. 35. Roll out. Normal conditions. During the rollout, the rudder pedals will be used to steer the aircraft on the runway centerline. At high speed, directional control is achieved with rudder. As the speed reduces, the nose wheel steering becomes active. However, the NWS tiller will not be used until taxi speed is reached. Crosswind conditions. The above-mentioned technique applies. Additionally, the flight crew will avoid setting side stick into the wind as it increases the weathercock effect. Indeed, it creates a differential downforce on the wheels into the wind side. The reversers have a destabilizing effect on the airflow around the rudder and thus decrease the efficiency of the rudder. Furthermore, they create a side force, in case of a remaining crab angle, which increases the lateral skidding tendency of the aircraft. This adverse effect is quite noticeable on contaminated runways with crosswind. In case a lateral control problem occurs in high crosswind landing, the pilot will consider to set reversers back to rev idle. At lower speeds, the directional control of the aircraft is more problematic, more specifically on wet and contaminated runways. Differential braking is to be used if necessary. On wet and contaminated runways, the same braking effect may be reached with full or half deflection of the pedals. Additionally, the anti-skid system releases the brake pressure on both sides very early when the pilot presses on the pedals. Thus, if differential braking is to be used, the flight crew will totally release the pedal on the opposite side to the expected turn direction. 36. Tail strike at touchdown. Although most of tail strikes are due to deviations from normal landing techniques, some are associated with external conditions such as turbulence and wind gradient. Deviation from normal techniques. Deviations from normal landing techniques are the most common causes of tail strikes. The main reasons for this are due to allowing the speed to decrease well below VAPP before flare. Flying at too low speed means high angle of attack and high pitch attitude, thus reducing ground clearance. When reaching the flare height, the pilot will have to significantly increase the pitch attitude to reduce the sink rate. This may cause the pitch to go beyond the critical angle. Prolonged hold-off for a smooth touchdown. As the pitch increases, the pilot needs to focus further ahead to assess the aircraft's position in relation to the ground. The attitude and distance relationship can lead to a pitch attitude increase beyond the critical angle. Too high flare. A high flare can result in a combined decrease in airspeed and a long float. Since both lead to an increase in pitch attitude, the result is reduced tail clearance. Too high sink rate, just prior reaching the flare height. In case of too high sink rate close to the ground, the pilot may attempt to avoid a firm touchdown by commanding a high pitch rate. This action will significantly increase the pitch attitude and, as the resulting lift increase may be insufficient to significantly reduce the sink rate, the high pitch rate may be difficult to control after touchdown, particularly in case of bounce. Bouncing at touchdown. In case of bouncing at touchdown, the pilot may be tempted to increase the pitch attitude to ensure a smooth second touchdown. If the bounce results from a firm touchdown, associated with high pitch rate, it is important to control the pitch so that it does not further increase beyond the critical angle. Aircraft system for tail strike prevention. The following aircraft systems help to prevent tail strike occurrence. A. Pitch, synthetic voice sounds when the pitch attitude becomes excessive. A tail strike pitch limit indicator appears on the PFD to indicate the maximum pitch attitude to avoid a tail strike. The pitch, synthetic voice sound takes into account the actual pitch value and the pitch trend. This can lead to pitch, synthetic voice sound to be triggered before any PM callout, or before the pitch reaches a high attitude on the PFD. This design is installed as an option on A320 and A321. Bouncing at touchdown. In case of light bounce, maintain the pitch attitude and complete the landing, while keeping the thrust at idle. Do not allow the pitch attitude to increase, particularly following a firm touchdown with a high pitch rate. In case of high bounce, maintain the pitch attitude and initiate a go-around. Do not try to avoid a second touchdown during the go-around. Should it happen, it would be soft enough to prevent damage to the aircraft, if pitch attitude is maintained. Only when safely established in the go-around, retract flaps one step and the landing gear. A landing should not be attempted immediately after high bounce, as thrust may be required to soften the second touchdown and the remaining runway length may be insufficient to stop the aircraft. 37. Flare mode A320 CEO. When the aircraft passes 50 feet raw, the THS is frozen and the normal flight mode changes to flare mode as the aircraft descends to land. Flare mode is essentially a direct stick-to-elevator relationship with some damping provided by the load factor and the pitch rate feedbacks. The system memorizes the aircraft's attitude at 50 feet, and it becomes the initial reference for pitch attitude control. As the aircraft descends through 30 feet, the system begins to reduce the pitch attitude to -2 degrees nose down over a period of 8s. Consequently, to flare the aircraft, a gentle nose-up action by the pilot is required. 38. Flare mode A320neo. When passing 100 feet raw, the THS is frozen and the normal flight mode changes to flare mode as the aircraft descends to land. The flare mode is a direct stick to elevator law without auto trim, with some damping provided by load factor and pitch rate feedback. The flare law provides full elevator authority. The flare law does not compensate for the thrust effect, and partially compensates for the ground effect. 39. Refueling with one engine running where applicable. The specific procedure for refueling with one engine running may only be used under the following conditions. A. Only applicable when no passengers on board the aircraft during refueling. B. The APU air supply function is unserviceable and there is no external ground pneumatic air available. C. Authorization from the responsible airport authority is obtained. D. An appropriate airport firefighting vehicle and personnel stand by at the aircraft during the entire refueling procedure. E. One flight crew member must remain on the cockpit to monitor the operating engine. F. An engineer is present at the aircraft fueling station, and 9. The aircraft refueling system is fully operational. Over wing filling is not permitted. 40. Engine failure at low speed. If an engine failure occurs at low speed, the resultant yaw may be significant, leading to rapid displacement from the runway centerline. To regain or maintain directional control on the runway, it is necessary to immediately reduce both thrust levers to idle, which will reduce the thrust asymmetry caused by the failed engine. To select both reversers irrespective of which engine has failed. To use rudder pedal for directional control, supplemented by symmetrical or differential braking if needed. The steering handwheels may be used when taxi speed is reached. Note: if rudder pedal input and differential braking are needed, apply both on the same side. Below 72 knots, the ground spoilers will not deploy and the auto brake will not activate. 41. Wake turbulence separation. Separation by time non-radar. Wake turbulence separation minima given below define a minimum separation time between two aircraft during takeoff and landing to cope with wake turbulence. Arriving aircraft. Medium behind heavy aircraft, 2 minutes. Departing aircraft. The minimum separation time is 2 minutes for a light or medium behind heavy or light behind medium. Two parallel runways have no influence upon each other if they are separated by more than 2,500 ft and if the flight path of the second aircraft does not cross the flight path of the preceding aircraft. Departing and landing in opposite direction, the minimum separation time is 2 minutes. Non-radar separation. When approaches are separated by time intervals of 2 minutes by heavy aircraft, if followed by a medium aircraft, and 3 minutes if followed by a light aircraft. In cruise. Wake turbulence may be encountered in cruise, where aircraft flying in the same direction are vertically separated by 1,000 feet only. In this case, if considered necessary, The pilot may offset from the cleared track by up to a maximum of 2 nm in order to alleviate the effects of wake turbulence. ATC should be advised if this contingency action but will not issue clearance for any such lateral offset. The aircraft should be returned to cleared track as soon as the situation allows.